You had your breakfast, Shobna?
No, I am doing intermittent fasting these days, so I don't have breakfast.
My goodness. Anyway, you've lost weight. Don't worry. So, shall we start?
Yes,
Yes, Bulu.
yes.
Yeah. Okay. Okay. So, a very good morning to all of you. Myself, Bulumani Kalita, Assistant Professor in the Department of Physics, Dibrugarh University. I take this opportunity to wish all my teachers, mentors, guides, and my dear colleagues a very happy Teachers' Day. Respected Dean, Research and Development, Dibrugarh University, Professor Deepak Setia sir. Today's speakers, Professor Shobana Narasimhan Madam from JNCSR Bangalore, and Professor Mandar Madhukar Deshmukh sir from TIFR Mumbai. Director IQAC and Professor Department of Physics, Dibrugarh University, Kailan Bhia sir. Head of the Department of Physics, Dibrugarh University, Dr. Pankaj Dutta sir. Distinguished invitees, my dear colleagues, and dear participants joining the event through the YouTube live channel. On behalf of the organizers, I would like to welcome you to the Professor H.L. Das and Professor S.B. Singh Memorial Lectures. The Physics Department, Dibrugarh University, is organizing Professor H.L. Das Memorial Lecture since 2017 after combined memorial lectures through online mode on the auspicious occasion of this Teachers' Day. Accordingly, we approached two renowned physicists in India, Professor Shobana Narasimhan, who works on computational material science, and Professor Mandar Madhukar Deshmukh, who is an expert in experimental physics, especially in condensed matter physics. So they were kind enough to accept our invitations in short notice. We are very much thankful for their acceptance. I now once again welcome and thank all of you for joining today's event to make it successful. Now I would like to request Dean Research and Development, Dibrugarh University, Professor Deepak Setia sir, to kindly deliver his inaugural address. Sir.
Thank you, Dr. Budamani. Good morning to one and all present in this memorial lecture. Let me first wish you, all the teachers, a happy Teachers' Day. This is the very special day that we Indians we celebrate annually as Teachers' Day. Also, I want to wish that you stay safe, stay healthy, and stay active. My esteemed head of the Department of Physics, and other faculty members, the two resource persons for this memorial lecture, Professor S. Narasimhan and Professor M. Deshmukh, other invited guests, and dear participants. Let me first wish all the teachers again a happy Teachers' Day uh, for the service rendered to the nation in the memory of the great philosopher, come teacher, Dr. Sarvapalli Radhakrishnan, who not only in India guided the whole academic world at that time. This is a special day, and on this special day, this memorial lecture has been organized by the Department of Physics in the memory of two other teachers who served the Department of Physics, Dibrugarh University at one time, and they gave a shape to the Department of Physics at the at different stages of the growth of the department. First, let me just thank the two resource persons for their kind acceptance to be with us on this auspicious day, as well as to deliver their lecture in the memory of the two successful and very meritorious teachers who served this Department of Physics at one time. Professor A.S.L. Das was an experimental physicist, as I have been informed, and he was a very meritorious student and a successful teacher in his time. He served his Department of Physics from 1977 to 1981 for 5 years. Then he left for Guwahati University, served there till his retirement in 2005. Before coming to Dibrugarh University, he served at different capacities across the nation, across India, and also after his retirement from Guwahati University, he served in many universities and institutes across the nation. A.S.L. Das Memorial Lecture is being organized by the Department of Physics since last couple of years. And this time, another teacher who left us last year in October 2019 and also who served this department for a long period of 15 years, his name has also been combined with this memorial lecture. And we have today assembled here for this online platform for the A.S.L. Das and Professor S.B. Singh Memorial Lectures. Regarding Professor S.B. Singh, I can speak many things because he was a very close friend of mine. I joined in the Dibrugarh University in 1990, initially in ad hoc position. Then it was in 1991, I was promoted to a regular position. And Dr. S.B. Singh, he joined in 1992 at Dibrugarh University. So we were contemporary, and initially during the first few years, we shared many things, starting from the rented house to the university teachers' flats. He was very meritorious and a successful teacher, as I came to know from the students and his colleagues. He was so popular among the students and the faculty members that very frequently we used to discuss about his very good command in different subjects, not only in physics, especially in the computer science application of the computers. He was popular among the small kids also. We stayed few years in the teachers' flat of Dibrugarh University, and the kids fondly they call him as Single, means Singh uncle. He was popular among the small kids also. He left the Department of Physics, Dibrugarh University in 2007 to join in Manipur University, and he successfully continued his service till his expiry in 2019. It is really a very good occasion that, along with Professor A.S.L. Das, Professor S.B. Singh has also been remembered here in the form of this memorial lecture. Coming slightly away from this uh, memorial lecture, I want to just put few points before you regarding the education in the especially higher education in the nation. Uh, the data published by the HRD, Department of Central Government, a year back says there were more than 15 lakhs of schools which enrollment of 26 crores of students uh, in the school level. But while considering the higher education, we have 903 university and institutes offering higher education degrees, with 42,000 colleges and 3.7 crores of students, which is nearly 7 times less than the number of school students. I want to just put this point for this because where the other students have gone, it is not that all the students have got their jobs and they have been absorbed somewhere in the in some placement areas. The thing is that we have less number of higher educational institutes. That's why the number of enrollments in the higher education institutes are less. The government has taken number of steps to improve the status as well as the standards of the higher education institutes. A national assessment survey, uh, NAS for schools, NIF and NAC for higher educational institutes. That a lot of initiatives have been taken for digitalization of whole uh, systems, not only in education, of course, in other areas also. That way, there are digital initiatives like SWAYAM, National Digital Library, National Academic Depository, etc. And at national level, the examination organization has been formed with the name National Testing Agency (NTA), which is conducting a lot of the examinations in the country. While considering the national data with the data from Assam, in many cases we have a less number of higher education institutes. We have 21 uh, degree offering institutions and universities with less number of colleges. So enrollment in the higher education in Assam is lesser than the national level. Whatever it is, our continued efforts will be on to increase the number of students in the higher education level, and the government has taken up a lot of steps, of course. Uh, in the same way, if we just consider the research activities in the higher education institutes, uh, definitely we have to put a very serious look into the research activities, not only in Assam but also in the national scenario. Uh, Regarding the two topics that will be covered by our resource persons, I consider these are hard topics of physics. I do not want to put any comment on these topics because I don't have knowledge. And if I say I have very limited knowledge on physics, they will take you to the very hardcore of the physics uh, uh, the area. I consider that the participants will be highly benefited. They will get a lot of information from these uh, invited lectures. I thank the Department of Physics, HOD and other faculty members for inviting me and for giving me this opportunity to be with you on this day and giving this opportunity to speak a few words before you. Hope the memorial lecture will be very much successful. The participants will get a lot of things from these two lectures. I thank especially the two invited resource persons for their kind acceptance. Uh, with this, I do declare that the memorial lecture has been inaugurated, and I want to conclude my inaugural speech. I wish a very successful and fruitful uh, deliberations during the lectures. Again, I wish all of you that you stay safe, stay healthy, and stay active. Thank you.
Thank you, sir, for your valuable information regarding the education system and the importance of online modes in the teaching learning process. It was also good to get brief introduction about Dibrugarh University from you, sir. Thank you very much. I would now like to request the head of the Department of Physics, Dibrugarh University, Dr. Pankaj Datta, sir, to say a few words.
Thank you, Bulawani. A very good morning to all present over here. Respected Professor Deepak Setia, sir, Honorable Dean, Research and Development at Dibrugarh University, Professor Shubhna Narasimhan, Madam, JNCSR, Bengaluru, Professor Desmukh, sir, Department of Condensed Matter Physics and Material Science, TIFR, dignitaries, guests, invitees, scholars, and students who have joined us today. I would like to welcome you all for this Professor Isel Das and Professor S.B. Singh Memorial Lectures 2020, which is being organized in fond memory of two former great teachers of the department. We are happy that we could organize this auspicious event of the department on this very special day. I feel that this is a great way to celebrate the Teachers' Day. I wish all a very happy Teachers' Day. The Department of Physics, Dibrugarh University was established in 1967 with four teachers, Professor K.M. Khanna, Dr. K. Borua, Dr. B. Boisho, and Mr. P.K. Borua. Today, on this occasion, I would like to remember all the faculty members of the department whose dedication and sincere efforts, hard work had shaped the present Department of Physics, Dibrugarh University. Presently, we have 13 regular positions with 7 dedicated contextual faculty positions. So we are now a young brigade of teachers working hard for the betterment of the department and for the university. The department runs 5 years integrated MSc, MSc, PhD, and MPhil. The major research areas are condensed matter physics, astrophysics, high energy and cosmology, space and atmospheric physics, and electronics. About Professor Hiral Dasar, Dasar was a noted experimentalist, as was already mentioned by Bulumani and Deepak Setia, sir, and he was a very dedicated physics teacher. He was considered as one of the finest experimentalists of the region. He was known for his very energetic and enthusiastic teaching. Born in 1942 in Lakhimpur district, Assam, Professor Das passed his BSc in physics from Cotton College in 1965, MSc from Delhi University in 1967. Then he started his research work in condensed matter physics from the Department of Physics and Astrophysics at Delhi University. and he obtained his PhD in 1974. After PhD, for a few years he served as lecturer in several colleges of Delhi. Then he shifted to IISc Bangalore in 1977 for a very short period of time. Same year, in June 1977, Professor Das has joined our Department of Physics, Dibrugad University as lecturer. He served the department till 1981. As an experimental physicist, blessed with remarkable capabilities of hard work, he was very successful in establishing a laboratory for his own at the Department of Physics, Guwahati University. His studies were basically the thin film physics and the properties dependent on the thin film behavior of the material. In later years, he shifted to some work on the area of nanocrystals as well. 11 students obtained PhD under his supervision. A very simple person with tremendous capabilities, Professor Das was known for his very simplicity and his hard work. He has also served Inter-University Accelerator Center, Manipur University, Tezpur University at various capacities after his retirement as well. He was the founder of the physics department, Rajiv Gandhi University of Arunachal Pradesh. He passed away on October 4, 2016 at the age of 74. About Professor Sanasam Brajamani Singh sir, popularly known as SB Singh sir, he has been a brilliant teacher and researcher of the department who passed away last year only. Though his specialization was theoretical solid-state physics, he holds brilliance both in experimental and theoretical aspects as well as other areas of the subject. His field of teaching and research encompassed mathematical as well as physical sciences. He rendered his services to the Department of Physics, Dibrugad University for a long 15 years, from February 1992 to May 2007, before shifting to Manipur University, where he had served as professor till his untimely demise. His research interests were chaos, nonlinear dynamics, fuzzy logic, and magnetosphere and space physics. He had 28 reputed publications. During his 27 years of association with the field of higher education as teacher and researcher, Professor Singh had contributed a lot for the administration of higher education as well as for academics. As Bulumani has already mentioned, this time only we are organizing this combined lecture. So I personally feel very fortunate as I was a direct student of Professor S.L. Dasar during my MSc, and also I could serve the department as colleague of Professor S.B. Singh sir for 2 years from 2005 to 2007. We are grateful, very grateful to our honorable speakers, Professor Shobhana Narasimhan Madam and Mandar Deshmukh sir, for giving their valuable time and with us for this particular lecture. I am thankful to all those participants who have joined us for this very special occasion. I am sure all the participants will be highly benefited by the words of these two very experienced, noted Indian scientists. I thank all the participants for being with us. I hope this lecture will be a great success. Thank you all. Over to Bulumani. Bulumani. Hello?
Yes, yes.
Yeah.
Thank you, sir. Can you hear me? So thank you, sir. So we are now moving towards the lectures of today's event. Before that, let me make a special announcement. After each presentation, there will be maximum of 15 minutes time for interaction. The participants can raise their queries through the chat box panel towards the right-hand side in the YouTube live streaming, from which selected number will be attended. The members present in the Google Meet can directly interact within the limited time allotted for that. So the first lecture will be delivered by Professor Shobhana Narasimhan. Before that, I would like to introduce the speaker to you. Professor Shobhana Narasimhan is a professor of theoretical sciences at the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, India. Her main area of interest is computational nanoscience. Professor Narasimhan earned her BSc in Physics from St. Xavier's College, Mumbai, MSc in Physics from IIT Bombay. She received her PhD in theoretical physics from Harvard University in 1991. Subsequently, She did her postdoctoral work at Brookhaven National Laboratory, USA, and at Fritz Haber Institute of the Max Planck Society in Berlin, Germany. She joined the Theoretical Sciences Unit of JNCSR, Bangalore, as a faculty member in 1996. She was formerly chair of the Theoretical Sciences Unit and Dean of Academic Affairs at JNCSR, a fellow of the National Academy of Sciences India 2011, and a recipient of the Sri Shakti Samman Science Award 2010 and the Kalpana Chawla Women Scientist Award of the Government of Karnataka in 2010, Professor Narasimhan has been elected as the International Honorary Member of American Academy of Arts and Sciences that recognizes the distinguished work of scholars and leaders in the field of art, science, and humanity and public life. Professor Narasimhan has actively involved in the development programs that encourage women to be a part of the sciences. She has supported the promotion of women in science, technology, engineering, and mathematics, STEM, in India and abroad. She also became the member of two committees set up by the Government of India, the National Task Force on Women in Science and the Standing Committee on Women in Science, and advised the government on how it can support the cause of women scientists. Apart from this very brief introduction, I would like to add here that Professor Shobhana Narasimhan is a very good teacher. She has excellent presentation skills. I am sure that all the participants will be mesmerized by her lecture today. So without delay, I would like to request Professor Shobhana Narasimhan to deliver her talk on computing the properties of materials from First Principles. So, Madam, I request you to start your presentation.
Professor Deepak Chetya, uh, Professor Pankaj Datta, Professor Bulumoni Kalita, Professor Mandar Deshmukh, Faculty of Department of Physics, and friends. Happy Teachers' Day to everybody. I'm honored to be asked to give this lecture. And also thank you, Bulumoni, for this very nice introduction. I hope I can live up to it. I just want to check that you can all see my screen. Bulumoni, can you see my screen?
Not yet.
Okay, I have shared it. So you still can't see it?
Not yet. Just
Okay,
give
then
it once.
maybe I have to share again then. It says can't share your screen. Okay, of course it will work when you practice, but not when you try. So we'll
Yes.
try again. Now can you see my screen?
Not yet. Yes, yes, it is coming. Pankaj,
Hello?
Professor Bulmani, maybe you can tell her that if she is using a particular browser, Chrome is better for this. I don't know what she's using, a Mac or a Windows.
Because sometimes the firewall install also does not allow Google Meet to continue with presentation. That may be the problem. So what you can do actually, you can ask her to mail the presentation to you, and Dr. Kolita may actually hold
she is out of the presentation and she is not allowed to enter it. So let me send her the link again.
Okay, okay. So sometimes what happens is if firewall is installed in the computer, then presentation is not allowed in Google Meet. That is the problem. I faced a lot of in a lot of occasions that problem, and so maybe that is the problem with her also.
I'm back at least at the meeting. Now let me try to see if I can share the screen. Okay, I think.
Yeah, it is coming now.
Yeah, now you can see my screen. I'm very sorry about that.
It's okay.
Okay, now let's get rid of this. Oh God, this thing's driving me crazy. Won't let me do full screen.
It will just push this other window out.
Yeah, I'm trying. I'm trying. Every time I click on that window, it goes back to the call. Okay. Okay. All right. Very sorry about that. Okay. So I'm going to talk today about computing the properties of materials from first principles. So where I'm from the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. And just to boast a little bit, we're a small institute, but last year when Nature Index ranked institutes in the world normalized by their size, we were pleasantly surprised to find that we were apparently ranked 7th in the world. So we were very proud of that. So I had the computational nanoscience group at JNC. So this is my group. And I want to first tell you a little bit about materials and why they're important and why it's nice to calculate their properties. So materials define human history and progress. Materials are so important to human life that we measure the progress of civilization by what materials were used in that civilization. So you have the Stone Age, the Copper Age, the Bronze Age, and the Iron Age, etc. And my students told me that nobody would understand what was the joke in this cartoon, which is that the Iron Age guy is called the Iron Age because he's ironing. So they made me put in this little laughing guy here to point to the iron. I will come back to the Bronze Age in a minute because I think the Bronze Age is especially interesting for certain reasons. How many materials exist in nature? This is, of course, the periodic table. And there are 98 naturally occurring elements. And out of these elements, There are 4,000 naturally occurring minerals, but of course, there are also a lot of man-made minerals, and you don't call them minerals, man-made materials. And that is what is of special interest to the material scientist. So we can make new materials. You might recognize that what has been made out of these Lego blocks in this picture is a periodic table. And if you're a material scientist, then the periodic table is your playground, it is your toy box, and out of the elements of the periodic table, you can make new materials. So that is what is of special interest to the material scientist. Now, I said that the Bronze Age is of special interest to a material scientist because the Bronze Age is different from the Stone Age, from the Copper Age, the Iron Age, etc. And that is because the Bronze Age is a result of materials design. Because bronze, unlike stone and iron and copper, is not a material that exists naturally in nature. Bronze is an alloy of copper and tin, and it has certain advantages. For example, it is harder than copper alone. It does not rust, unlike iron. And the amazing thing is that already in these prehistoric times, people had realized that they could make this alloy which had these superior properties. So, this is an artist's depiction of guessing how they might have made bronze in those times. And these are some bronze artifacts from ancient India. You might recognize this figurine of the dancing girl of Mohenjo-daro. We said we had to study about it in school. And it's a very beautiful small statuette, which is made of bronze. But what is fascinating to think about is how did they know already at that time that if they made this alloy, it would have superior properties? Or all the materials that we use today, how did people know that if they mix this metal with that metal, it would have certain superior properties? Now, nearly all the materials that we use today have been found in one of two ways. They were either accidental discoveries or people found by trial and error. So I put two cartoons here, which are sort of joking about how one might have made another famous prehistoric discovery, which is the discovery of the wheel. Maybe the wheel, it is speculated, was found accidentally, like somebody made a circular form out of stone for some reason, and then it rolled, and then they said, oh, maybe we've discovered something. Or they wanted to make something that would roll, and they tried a square, a triangle, a circle, etc., and then said, oh, we found it. Okay, so maybe for bronze, the same way, they accidentally made something, or they kept trying and they finally found what works. Now, um, for the trial and error approach or the brute force approach to material synthesis, of
Actually, she has some internet issue. Shobna, you are mute.
Okay,
Yes.
can you hear me now?
Yes, yes, yes.
Okay. I'm really, really sorry. Today's just been a day of disasters. My internet, of course, died a minute ago, and then I had to switch to another connection. So, I talked about the brute force approach to materials discovery. So that is, you just try things one by one by one. So a famous example of that is the Haber process for the synthesis of ammonia. So you want to synthesize ammonia from nitrogen and hydrogen. And this is one of the really famous reactions. It is considered very important because the productivity of agriculture shot up hugely once people knew how to make ammonia as a fertilizer. And you may know that iron is used as a fertilizer, but as the catalyst for this process. But before they knew to make iron as the catalyst, they systematically tested about 4,000 materials for the catalyst before they decided to use iron. In fact, they found that a better catalyst is osmium, but osmium is rather expensive, and they therefore decided to use iron. But this is obviously a rather uh, painful and tedious way of finding the best material. So, what we want to do now in material science is, instead of using this trial and error or brute force method, is to use what people call rational materials design. And for rational materials design, you need to have a to and fro between theory and experiment. So, I am a theorist. So, what do you do if you're a theorist and you want to do rational materials design? So, you take maybe three materials, say material A, material B, material C, you do computations on them, you analyze these computations, and you try to understand why these materials have the properties they do. And once you have understood that, then you can design on the computer a new material with desired properties. So, why do we do computations rather than just do experiments? It is cheaper. In fact, nowadays computers are becoming so fast that maybe you need just a laptop. I thought that in coronavirus times, it is an advantage that you can work from home. It's often quicker to do the computation. Sometimes the computing can lead to greater understanding. You can simulate conditions on a computer that can be very difficult to achieve in the lab. You can switch off in a calculation certain effects, and you can make predictions for experimentalists to verify. I do want to emphasize, however, that all of this has to be done in collaboration with experimentalists, And the ultimate test of any calculation is always the experiment. So I said conditions that are hard to achieve in the lab. So this might be, for example, if you want to know what is the properties of, say, the iron at the center of the Earth's core, then obviously this is something that you can't really do the experiment very easily. But in a calculation on a computer, you can simulate those conditions much more easily than you can in an experiment. So the technique that we use in my group and in many other groups is called density functional theory. So I'll tell you a little bit about that now. So when you want to compute the properties of a material, the basic physics problem that you're trying to solve is called the quantum many-body problem. So this problem ultimately boils down to the fact that you want to solve the properties of a problem which contains a certain number of nuclei and a certain number of electrons. And these are all interacting via the Coulomb interaction. So examples of systems like this are atoms, molecules, condensed matter systems. And for these, to compute their properties, you have to solve the many electron Schrodinger equation. And we have this condition that the solutions for this must be properly anti-symmetrized to satisfy the Pauli exclusion principle.
I think she's having internet issue. I am contacting her.
Okay, I guess I'm back. Can you hear me now?
Shobana, one thing you can do is email me your slides. It's okay.
Yeah,
The
but
slides.
if I can't see the slides, how do I give the talk? It keeps kicking me out of the call. I don't know why. I've never had such a problem before.
Okay, that's okay. What OS are you using? Mac or Windows?
Windows.
And is your browser Chrome?
Yeah.
Okay. Then it should be okay.
But I had the
Okay,
same
all right.
problem yesterday. We had a faculty meeting in Google Meet and it kept kicking me out.
Okay. Yeah. Anyway, you can try again. It might be okay.
I'm going to try one more time, and if this happens again, I'll just cancel the talk. I don't know what else to do.
Okay, try it.
Okay, so I don't know when I was cut off last time. So what was the last slide you saw? Did you see this slide?
No, after that.
You saw this?
Yes, you go ahead.
You saw this?
Yes.
You saw this?
No.
Okay. I'm just going to skip this and go on to this. Okay, so the many-body Hamiltonian is that you have the kinetic energy of the nuclei, the kinetic energy of the electrons, the potential energy between the nuclei, the potential energy between the nuclei and the electrons, and the potential energy between the electrons. And it is this that makes it difficult. And density functional theory is a way of including the troublesome electron-electron interactions. And how it does this is it maps the many electron problem onto an equivalent one electron problem. So what it does is, this is an analogy. So in this picture, the blue people are like the nuclei and the red people are like the electrons. And it's a many-body system with very complicated interactions between them. And it is the problem you have is you have to arrange this group of people so that you achieve an optimal level of happiness, which is obviously a very difficult thing to do. So instead, what you do in DFT is you map this problem exactly onto this system where you still have many blue people, but you have only one red person, one electron, and you have to move her so that you have again the optimal level of happiness. So this is obviously a much easier problem to solve. But the remarkable thing is that the solution to the problem on the right is the same as the solution to the problem on the left. Now, when you do this mapping, obviously something has to change. There is a certain complication. And this complication I have represented by putting face masks on these blue men. So these face masks are what are called the exchange correlation potential. So there is a new term in the potential, which I have represented here by these face masks. So the problem looks a little bit different. So the person who invented all this is called Walter Cohn. And for discovering all this, to find this way of approaching the problem, it was so important and such a remarkable achievement that he was given the Nobel Prize in 1998. And density functional theory has proved so successful and so popular that in the PhysRev journals, if you look at the 10 most highly cited papers, they are all to do with DFT. Of course, it sounds too good to be true that you can map this many body problem on exactly onto a one body problem. And in some sense, it is too good to be true, because to map this problem onto the one body problem, you have to design the perfect mask. You have to design this perfect exchange correlation potential so that this mapping is exact. And the problem is that we haven't yet designed this perfect mask. We haven't found this exact exchange correlation potential. And so there is a huge uh, reward, almost certainly a Nobel Prize guaranteed to somebody who succeeds in doing this. But so far, we have very good guesses for what this potential is, and that is why we're able to do DFT calculations. So first principles calculations is what we also call density functional theory calculations. So they're also called ab initio calculations. And the reason for that is that the only input into the calculation is the atomic numbers and the atomic masses, and everything else just comes out. You crank the machinery of DFT and then you get this output. So what is this output that comes after you do the calculations? You get very accurate results for the total energy of the system and other properties of the system. So what are these things you get? You get the total energy, which is a very useful quantity. You can use it to calculate the geometric structure, and you can also get the charge density. Now, these are the two things, the total energy and the charge density, which are guaranteed to be exact. You also get electronic energy eigenvalues. Now, you notice that I put a smiley face next to these two, but a sort of doubtful face here. And that is because the electronic eigenvalues are not guaranteed to be exact, but we still make use of them anyway. And DFT codes can be run on many platforms. And because computers are getting so fast, you can certainly run them on a laptop, though for very large systems, of course, you need a supercomputer. And this picture shows that one of my friends, Nicola Marzari, even managed to get a DFT code to run on his smartphone. So let me give you some examples of computing the properties of materials from first principles. So this is to show, first I want to tell you how accurate are these calculations. So I talked about bronze, which is an alloy of copper and tin. So let's see how accurately can you decide whether you can make an alloy. So what is shown in this triangle is here are lots of elements, and here again are the same elements. And let's see, can you make an alloy out of these two? That is, if you mix these two elements, will they mix or will they not mix? So the color here shows whether they mix to form an alloy or not. So these are all results of DFT calculations. And here, if it's a green circle, it means that both experiment and theory tell you that they mix. If it's a gray circle, which looks sort of white on the screen, it means that both experiment and theory tell you they do not mix. And you see that most of the triangle is either green circles or gray circles. And so the calculations are pretty exact for most of it. But there are some red triangles where the calculation tells you that they mix, but the experiment tells you they don't mix. So it is a fairly accurate technique, but it is not perfect. The experiment and theory mostly agree, but not always. So now can you design a material, or can you find a material for a certain application? So the application that I'm going to discuss here next, this is not my work, this is the work of somebody else, is you may know that we want to work on a hydrogen economy. That is, you want to use hydrogen as a fuel for cars, for example. How do you generate this hydrogen? One possible way is to generate it from water by splitting water into hydrogen and oxygen. And to do this, you need a catalyst. So this catalyst has to have certain properties. For example, it should be stable into splitting into its constituents. So you should be able to make the constituent. And if you want to use it by using light as the source of energy for the splitting, then it should have a band gap which should be in a certain range. So here is this calculation that people used, performed again on a class of materials called perovskites. So these are AbO3 perovskites. And these are all possible sources for the A metal on one axis and all possible sources for the B metal on the other. And they did calculations on these 2,601 compounds. And they calculated the heat of formation and the band gap. And when they finally calculated these two quantities, only 10 out of these 2,601 compounds remained. And once you have narrowed this down to these possibilities with the calculation, then the experimentalists can try to make only these 10 compounds. Another famous example of something that was found by DFT is, you may know that diamond is the hardest material known to us. But these two scientists, Amy Liu and Marvin Cohen, showed that if it were possible to make this material called beta carbon nitride, then it should be harder than diamond. So this discovery of theirs, this prediction, got a lot of attention. Unfortunately, though people have made it in tiny nano-sized quantities, so far people have not succeeded in making larger size samples of this beta carbon nitride. I had mentioned to you that one advantage of density functional theory is that you can study, using density functional theory, the properties of materials in conditions that you cannot reproduce in the lab. So though this is not quite materials for certain applications, I think it's very interesting to know what properties matter has, for example, at the center of planets. And there's some very interesting discoveries people have made in this context. For example, they have found that in the center of Jupiter, the hydrogen is a metallic fluid. In the center of Neptune, they believe that it's carbon, which is the form of a huge diamond. And for Earth, at the center of Earth, they believe the material is twice as hot as we initially thought it was. Now I'm turning to my research, and I want to give you two examples from my research. So the first example I want to give you is some work we did quite long ago, but I think it's sort of easy to explain. So I want to tell you about tuning the morphology and catalytic activity of gold nanoparticles by substrate doping. So doping is when you add a little bit of a foreign element into a material and change its properties. So this picture here shows this famous Turkish chef called Salt Bey. He's famous for cooking things and adding a little bit of salt at the end. And salt is something you add just a little bit and it changes the taste. So doping is like that. Now, most of you would know that doping is something you use in semiconductors. You add a little bit of phosphorus or arsenic, and it makes it N-type or P-type, etc., and it changes the properties of the semiconductor. Doping is something that is still used a lot and has very important consequences in material science. For example, these three gentlemen found that by doping organic molecules, you can make conducting polymers. So for this, they were given the Nobel Prize in 2000. And these three people found ways of p-doping gallium nitride and thus making blue LEDs, which is something people had been trying to make for a long time. And for that, they were given the Nobel Prize in Physics in 2014. I want to tell you about gold. Gold is something, of course, everybody is very familiar with for jewelry, uh, as an investment, etc. And gold is something people always thought was chemically inactive and inert. But in 1987, the surprising discovery was made that if you have gold in nanometer sizes, if you have gold nanoparticles, then gold becomes extremely reactive. This set off what people call the gold rush. So in this graph, what is shown is the number of publications containing the keyword gold nanoparticles as a function of year. And you can see that as time went on in recent years, the number of papers on gold nanoparticles published every year has increased hugely. So what do gold nanoparticles look like? If you have really small nanoparticles of gold, then the way the atoms are arranged in these nanoparticles may or may not look at all like the way they are arranged in a bulk gold crystal. In a bulk gold crystal, they're arranged in the FCC structure, which is the face-centered cubic structure. But in a gold nanoparticle, they may be arranged quite differently. For example, in this 13-atom gold cluster, they're arranged in an icosahedral shape. So larger gold nanoparticles have a three-dimensional shape. However, there's reason to believe that they will be better catalysts if they can instead be made to take a two-dimensional flat shape. So our main goal is to flatten the curve. Okay, sorry, that's not quite right. Flatten the curve is, of course, a expression that we use a lot nowadays in the context of coronavirus. Our goal is to flatten the nanoparticle. So we're saying that in normally, if you have a gold nanoparticle, say 20 atom gold crystal, a gold nanoparticle, then this three-dimensional shape is lower in energy than this two-dimensional shape. And we want to know, is there some way to flip this seesaw so that this flat shape becomes lower in energy than this three-dimensional shape? So previous authors have suggested various strategies. So this is again a joke about coronavirus times that if you just wait, then the curve always flattens. So our suggestion was that doping is something that achieves this. So if you deposit this gold nanoparticle on magnesium oxide, which has been doped with aluminium, which is an electron donor, we predicted that this flattening would happen. This is a picture of my student Nisha Maman, who did this work. And if you look closely, you will see that she's wearing two earrings, which are these two forms of the gold nanoparticle. This is the three-dimensional shape, and this is the two-dimensional shape. And we showed that if you calculate the total energy of this gold nanoparticle as a function of the doping concentration, then as a function of the doping concentration, beyond a certain doping concentration, the planar form is favored over the three-dimensional form. And people in Germany, a group of Freund in Berlin, did this experiment. And they found that if you deposit the gold nanoparticles, these are scanning tunneling microscopy experiments, if you deposit it on an undoped substrate, it has a three-dimensional shape for the gold nanoparticles, Whereas if you deposit it on a doped substrate, then the nanoparticles become flat. So this is a case where a prediction on how to design a material was made by density functional theory, and then people did the experiment and the prediction worked. And why does this flattening happen? It happens because when you deposit it on the doped substrate, there's some extra electrons from the electron donor, and these electrons are transferred to the nanoparticle, and then to lower its energy, the nanoparticle flattens. So I told you that the reason we want the nanoparticle to flatten is to make a catalyst. So we want to check if it is indeed a better catalyst. So how do you see if something is a better catalyst? Now, a catalyst is something you use for a chemical reaction. So in a chemical reaction, what happens is you are somewhere in an initial state, say here, and you want to go to a final state, say here. So to go from here to here, you have to climb some hill, okay? So there may be different ways to go from here to here. And what you have to say is you want to find the lowest energy path to go from here to here. And the lowest energy path is this one over here, which is you go through this blue point, which is a saddle point, which is called the transition state in this energy landscape. So what a catalyst is it's a substance that increases the rate of a chemical reaction without itself being consumed in the chemical reaction. So say that without the catalyst, you followed this blue path to go from your initial point to your final point. With the catalyst, you can lower the energy and instead find a lower energy path, which is this magenta point. So what the catalyst does is it allows the reactants to absorb on the surface, and that gives a lower energy path so that the reaction can take place with lower energy. So to do this, we took our flattened gold nanoparticle and looked at a reaction. This reaction is the dissociation of an oxygen molecule. So these two blue atoms here are an oxygen molecule, which is absorbing on the surface, and then slowly the oxygen dissociates. You can see that the blue atoms are getting further apart and dissociating. And we can calculate the energy for this dissociation to occur with density functional theory. And we do indeed find that the energy barrier that has to be climbed when you have the undoped surface and this three-dimensional particle is 0.68 eV. But when you have the doped surface and this flat particle, the barrier is reduced by more than half. So this is indeed a better catalyst, and you have found a way of making a better catalyst. Now I will talk about another example from my research to tell you that you can also study dynamics. So for nanoparticles, you also want to find out how they move on surfaces. The reason is when you have these nanoparticles on surfaces, for example, as catalysts, you want them to stay. You don't want them to diffuse and move and form nanoparticles, larger nanoparticles, etc. So you want to find out ways of stabilizing them. So I just want to show you from another project that we did that we can find out how they move. So here, this is two platinum atoms. It's called a platinum dimer on an MgO surface. And you can see here that we have found from DFT that they don't move by a simple translational motion. Instead, they're moving by what is known as a cartwheeling motion. A cartwheeling motion is like what this woman is doing on the right here. She's moving by flipping, okay? She's not just running, she is turning upside down as she moves. Now, the interesting thing we found here is that the way a nanoparticle moves depends on the number of atoms in the nanoparticle. So, the previous slide, I showed you how the nanoparticle moves if there are two atoms in the nanoparticle. If there are three atoms in the nanoparticle, then you can see now this nanoparticle is moving quite differently. It is walking slowly, and this motion reminded me of the movie Star Wars. And in Star Wars, there are these vehicles called AT-AT walkers, which is what is shown in the right. And the three atom nanoparticle is moving like an AT-AT walker. And we can also calculate here the energy barrier for this motion. Okay. So we can see how what the energy is at different parts of this motion as the particle moves along. So we know also how much energy it costs for the particle to diffuse along the surface. What happens if you now add one more atom to the nanoparticle? If you have four atoms in the nanoparticle, then again you have a third kind of motion. Now it is a kind of rolling motion. So here you have a rolling motion, and again you have a different energy barrier. So I just wanted to show you some examples to show that you can also study dynamics and not just static energies. So that is all I wanted to show you. I'm extremely sorry that the internet kept going and I kept getting kicked out. I have never had such a bad experience of giving an online talk. I really apologize very much. Uh, Thank you very much. And I can now take questions.
Thank you, Shobana. So, although there was a little bit of technical problems in between, but I'm sure I was right. I rightly stated that your presentations are really very interesting. Participants must have many questions who are attending through YouTube channel. So I would like to request Dr. Gauri Shankar Das if you can quickly transfer some of the queries from the live channel to here. And moreover, the panelists in this Google meeting, they can also directly interact with Professor Shobana.
Gauri, please unmute your mic. Gauri, please
Yes.
unmute your mic.
Yeah, first of all, thank you, Gulumani. And thank you, madam, for this wonderful talk. It was visually very appealing because some of the topics were such that it has to be always better understood if you explain through cartoons and some kind of animations. So really, it was a very wonderful talk and equally very appealing presentation, as I have said. Now, let me move to the questions. So now I'm scrolling to the page of YouTube. So I can't see any questions here. So maybe the panels which is now present at the moment live through Google Meet, they can have questions. So I can see Indrajit Sharma. So if you have any questions, you can unmute your video and microphone and ask your questions. So Indrajit Sharma.
Yes, good morning, Madam Shobana.
Morning.
Shobana, this is Professor Indrajit Sharma from Assam University, Silchar. Okay. I am also working DFT. Mainly, I do work on theory and some little bit on computation. My question is like this. Doing the computations in the department level is quite difficult. So I would like to know from you, how do I assess the computation facility in JNC or some other places in our country?
So We now have some computers available under the National Supercomputing Mission. And they've just been acquired, so I'm not sure what the procedure is, what procedure has been set up for people to access these computers, but I'm sure they will set up some procedures. So perhaps you can send me an email and I can direct you to the right person who can answer these queries.
So one second, only another one question, madam. Madam, can you throw some light how do we generate the structure of a thin film? My doubt is that when we generate the structure of a thin film, we put the vacuum. We put the vacuum ABC. See, we put generally 10 angstrom around. So when we do put the vacuum of 10 angstrom, how we are taking the entire ABC. Even we put the vacuum of 10 angstrom, we are taking the structure is ABC. So how it is happen? I am having doubt here.
Okay, so this is sort of a technical question.
Yes.
So there are different kinds of density functional theory codes, but what are very popular are what are called plane wave codes. These are codes which use a plane wave basis. And for technical reasons, if you use a code which has a plane wave basis, you have to use periodic boundary conditions. And then but you may have a system which is not periodic. And one example of a situation which is not periodic is if you have a surface, because the presence of the surface breaks the periodicity. So if you are doing something like a thin film or a surface where the periodicity is broken, then you make the system artificially periodic by saying that you have a thin film and then a vacuum region and then again the thin film and again a vacuum. And so you make an artificially periodic system by putting in this vacuum. And so you now have your lattice vector A and B, which are your lattice vectors of your thin film in plane. And the C vector is a very long C vector, which connects one thin film to the next thin film separated by a vacuum. I hope that answers your question.
Yes, but in that case, how do I take the unit structure? Because to start the DFT code,
maybe why don't you contact me for this? Because I think this may not be of interest to people who are not working in DFT.
Yes.
But I'll be happy to answer your question.
I will drop an email, madam.
Yeah.
Later on. Thank you. Over.
Okay, so thank you, Sharma, for your questions.
Shobna, there is a question sent to me directly by a research scholar. I am a learner in Quantum Espresso. So I am doing magnesium oxide monolayers. And does the band structure depend on the pseudopotentials?
In principle, it should not. So if you have a good pseudopotential, then it should not depend on this. Okay, so again, these are all very technical questions. Pseudopotentials are something where you consider only the valence electrons. So it will depend on the fact that you're using a pseudopotential in the sense that you will not get the band structure of the core electrons, you will only get the band structure of the valence electrons. But if you have chosen your pseudopotential properly, then if you go from one pseudopotential to the next pseudopotential, the band structure should not change.
Okay. So if there is no more question, if anyone wants to ask something here. Okay, if there is no more question, let us thank Professor Shobhana Narasimhan in spite of the little bit of technical issues that she faced. Actually, I feel sorry for that because she kept trying to basically.
I'm really, really sorry. I mean, this is the first time this has happened, that talk got interrupted. I mean, I've never had even one interruption, let alone 4 interruptions. It's just awful. Sorry.
But again, we have learned from coronavirus situation, right? It may have interruptions for months.
Yeah.
Yeah. So it was a nice presentation, Shobna, and I hope in near future we'll be able to learn from you again, especially our students. Thank you once again for giving the time here. So, uh, if I am
Thank you.
permitted, yeah, if I am permitted, then let us move to the next most awaited talk of the today's event, which will be given by Professor Mandar Madhukar Deshmukh of TIFR Mumbai. So before that, let me introduce the speaker to you. Yeah, Professor Mandar Madhukar Deshmukh is an Indian physicist specializing in nanoscale and mesoscopic physics. Professor Deshmukh is an experimentalist working in the broad area of condensed matter physics and material science. His research work focuses on diverse aspects of nanoscale physics with particular expertise in nanoelectronics. Professor Deshmukh joined as a faculty in Tata Institute of Fundamental Research, Mumbai in the year 2006. Presently, he is a professor in TIFR since 2017. He was awarded the Santi Swarup Bhatnagar Prize for Science and Technology in the year 2015, the highest science award in India in the physical sciences category. He obtained BTech degree from Indian Institute of Technology, Bombay in 1996 and PhD degree from Cornell University under the guidance of DC Ralph in 2002. Before coming to TIFR, he was a postdoctoral researcher at Harvard University. Professor Deshmukh, a Fellow of Indian Academy of Sciences 2019, is a recipient of many prestigious awards like Young Career Award in Nanoscience and Technology for the year 2018, awarded by Nanomission DST, Swarna Jayanti Fellowship 2012, etc. Unfortunately, I personally have not got the chance to hear from you, sir. We have heard about your nice presentations and are eagerly waiting for the same today. So without delay, I would like to request you, sir, to deliver your lecture. Sir.
Okay, thank you, all the members of the physics department and the university, and thank you, Professor Kalita, for inviting me to this interaction with your students and faculty to commemorate something very nice, which is the memory of and contributions of your past colleagues. So thank you very much for inviting me. It's a pleasure. So I'm going to tell you a little bit about our work, and I enjoy these interactions because the future of Indian science or science of any nation is actually the young students. They drive what happens to the community, the scientific community, and in particular, the students in India are extremely smart, and they come from very remote areas of the country, so I think that's one of the strengths of the Indian system. Okay, let me get started. Let's see. Hopefully, it'll be okay. Okay, so you should be able to see the screen. Is that okay? Can
Yes.
you see?
Yes.
Okay, great. Let me just. All right. Okay, so I'm going to tell you about sort of a broad overview and some bits of connection to our own research that we do in TIFR. As has been said earlier, I'm an experimentalist. And one of the things that I want to kind of convey through my talks is that experimental science is exciting, and we need lots of experimentalists. So if you're considering a career in physics or any science, I would say experiments are, we need you. Okay, so my talk will focus on 2D crystals, which are basically close to 1 atom thick. And I'll try to convey what is exciting about it. We gratefully acknowledge the funding support that we get from Department of Atomic Energy and Department of Science and Technology. Without this support, and this is the departments of the government, but they're effectively, through the people of India, their taxes make this research possible. So for that, I'm really grateful. So let me get started. Before I go into the actual part of the talk, science is a collaborative, everybody works together, students, researchers, young researchers, we are all kind of in it together, and there's really no hierarchy. And that's what makes this field exciting for me. And my students, some of these are kind of in this photograph that we took before a monsoon hike near Bombay. So if you're ever in a monsoon in Bombay or Bombay region, you should take a hike close to the mountains here. And so these guys are actually the people who do the work. This is their work, and I only am privileged to kind of make a presentation here. And many of them are very young people, many of you in the hopefully listening to this presentation. So I thank their contributions and many other collaborators in TIFR and elsewhere. Okay, so what do we do? So this is a broad overview of the work that we do. This is all experimental work. We study different kind of electronic devices. I'll show you some pictures later on. We try to study superconductivity introduced in graphene. So it's not really graphene, which is one atom thick graphite, is not really superconducting, but you can make it superconducting by connecting it to materials that are superconducting. So we study what is called as proximity Josephson junctions. Then we look at superconducting properties of high TC superconductor down to few unit cell. This I will mention a little bit. We study magnetic properties of two-dimensional crystals. We look at mechanics. So imagine, a drum. You have a tabla or a dhol, whatever you want to refer to it as. But now you make the drum with something which is only one atom thick, and its size is now much smaller. It's about 3 micrometers. So, which is much smaller than the drum, but you can still look at the vibrations of this drum. And we study this. And then we look at something that's kind of focus our work is how electrons flow through something which is very narrow to the extent that it's only 1 atom thick, or maybe 10 atoms, 20 atoms wide. So electrons flowing through this narrow region does not follow the regular description of classical mechanics, and quantum mechanical effects become dominant. Okay, so this is sort of the rough overview of what we do. I'm going to give you example of graphene related work. This is my outline for my talk. I'm going to tell you what is a 2D material, how does one call something 2D material. Then I'll talk about graphene, which is something that's in the public discussion even over the last several years because of the impact it has had on lots of different aspects of research. I'll tell you what graphene is and how few layers of graphene are interesting. Then, time permitting, I'll talk a little bit about 2D superconductors. Let me just make sure that I'm keep track of time. Okay, so this is my rough outline. It will show you where I'm going, and at some different point of the talk, I'll show this again to tell you where we are in this sort of journey. Okay, so now I want to start by asking a question. What is a 2D material? So people use this terminology. It's a 1D material, 2D material. Who decides it? Okay, so what I want to start off by saying is that this is a property dependent answer. So if I'm looking at electronic property or an optical property or a magnetic property, some system can be 2-dimension or reduced dimension based on the specific property. So something that's 2D for optics may not be 2D for electronics. Okay, so how does one think about it? So for electronic properties, for the case of electronics, which involves the flow of electrons, the de Broglie wavelength, which is essentially the extent of the wave function of the electron, or one way to think about is the Fermi wavelength it determines the dimensionality. So if something is smaller than the Fermi wavelength or of a material in which electrons are flowing, that dimension gets kind of compressed or reduced. So we live in a three-dimensional world, but if I make a three-dimensional cube thinner, so that in one direction it becomes thinner than the Fermi wavelength, then it becomes a two-dimensional material as far as the electronic properties are concerned. Okay, so that's really kind of key to understand. If you look at optics or magnetic kind of properties, then you have to ask some other sort of length scale whether the system is smaller than that or larger than that to determine the dimensionality. Okay, so I hope this kind of sets the course for why things are called reduced dimension. Similarly, you can think of something which is one dimension, which is if you confine something as far as the electronic properties go tighter than the Fermi wavelength in two directions, you become a wire, then it is called one dimension if the dimension in the two directions is less than the Fermi wavelength. Okay, now we have set the ground for what to call two dimension. So graphene is actually something that all of you are quite familiar with. If you have used a pencil, which I believe all of you must have at some point of your education, a pencil lead is made of graphite. Okay, so when you use your pencil, actually pieces of graphite are falling off and getting stuck to the fiber in your paper. Okay, now invariably it's a probabilistic event or a random event that sometimes 2 layers, 3 layers, 10 layers or 100 layers of graphite, thick graphite fall off. Sometimes one layer even falls off, but the thing is that you don't have an easy way to locate it. So in terms of definition, all of you have already done experiments with graphene. It's just that you didn't have full awareness of what where the graphene is on the piece of paper. Okay, so graphene is one atom thick graphite. Okay, so what its structure looks like is a honeycomb structure. It looks like this pattern repeats, and it's just made of carbon atoms at each of these orange and green sides. Okay. Now, there's a reason why I have painted green and orange at these two different sides. At a superficial level, the green and orange sides are identical. Okay, but if you look carefully, green and orange sides are very different, and that is intrinsic to the properties of materials. This is called the idea of symmetry, is intrinsic to a lot of studies in physics. And a simple answer to the question is, if you ask the site A, is there a site to the left of site A? And the answer is there is no site on the left of A, whereas of site B, there is no site available on the right side of B. So left and right, the fact that the left and right are not the same is kind of important. Okay, and this gives a different flavor to the physics of how electrons flow in graphene. So in case of graphene, both these sites are occupied by carbon atoms. In plane is a nice sp2 hybridized bond, and perpendicular coming out of the plane of your screen of your electronic device are p orbitals, which are unhybridized, and their sideways overlap creates a cloud of electrons called the pi orbitals, which is here and on the other side, which gives rise to the electronic properties. So these sp2 bonds create essentially the mechanical structure to keep the whole lattice stable, and the electronics is by different orbitals. So whenever we want to understand any system's electronic properties, what one tries to do is look at the energy momentum relationship of electrons which are flowing. So this axis is the energy axis, and this axis is the momentum axis. Okay, so in case of graphene, which is this honeycomb lattice, something peculiar happens, that you have a band, which is basically another way to say set of electronic states, which are sort of this curving as a function of the momentum, and you have another set of states which are valence states, which are these, which are exactly symmetrical, about this mirror plane which is here. So this is the conduction band and the valence band. And the Fermi energy is basically the energy up to which the electrons are filled in the material in its sort of pristine state. Now, whenever we want to understand electronic properties, because electronics that is all around us is essentially ripples of electrons on the top of this electron sea. There are lots of electrons in any material which are deep inside the electronic sea. They actually don't contribute to any electronic phenomena for electrical devices typically. So we care only what's close to the top of the sea. So electronic properties are like waves on the top of the electronic sea. And that's really, so we want to zoom in on top of this electron sea. So you do that, you have 6 points where the conduction band touches the valence band, but if you zoom in, it looks like a cone, 2 cones touching each other. This is, there is a lot of part of the band above, but that's not of interest, and so is the case below it. And this is the Fermi energy. So what is unusual and interesting about graphene is that the electronic states are meet at a point. So first of all, it's not a semiconductor. It's sort of closer to a metal. It's called a semi-metal. For some technical reasons, for now, let's kind of skip it. Maybe somebody will ask me a question about it. So what is interesting about graphene, and there are other materials like graphene, is that this energy momentum relationship is linear. And this is counterintuitive to us and interesting for physicists and other researchers, because everything around us in our everyday world, you look at a car or a ball or anything else, its energy and momentum relationship is quadratic. You say energy is proportional to p square for a ball or a car, whatever. But so most of solid state physics also follows that energy is proportional to momentum square. But in case of graphene, something unusual happens, and that's that energy and momentum relation is linear, okay, which is one of the interesting and unusual parts. And I'll explain a little bit down the line why this is unusual and interesting in comparison with the rest of the physics that we know. Okay, so now when you have a structure, this is energy and momentum of the electrons, which is allowed by quantum mechanics, then you can ask some questions about how many electrons are available at all energies. You can think of what are the possibilities of populating the electrons. So this shaded area tells you what are the seats available. So think of this plot as seats available for the electron to go and occupy themselves in an auditorium. So if there are no states available, then the electron cannot be there. Okay. So interestingly, in case of graphene, at this point, which is called the Dirac point, the density of states, essentially positions where they can go and sit in energy, are not there or becoming very, very small. And this point is called the Dirac point. In a moment, it will become a little bit clearer. And one can make devices. So one of the exciting things as an experimentalist is you can make electronic devices with graphene. And I'll show you pictures of the kind of devices we make in our lab, which are basically transistors. So imagine a sheet of graphene, and I'll show you what it realistically looks like. This is a schematic, and you make connections to it. So some of you may know of a field effect transistor that you might have learned in electronics or electrical engineering course. Now you can make another electrode, which is called the gate electrode, which electrostatically tunes the density of charge carriers. One simple way to think about it is that you take graphene as one plate of a capacitor and the gate as another plate of a capacitor, separated by this light bluish green dielectric, which is an insulator. Then as you apply a voltage to the gate electrode, you essentially charge this plate with one sign of carriers and the other gate electrode with the opposite sign. That's just a simple capacitor in play. So you can actually move this Fermi energy up and down by applying a voltage to the gate electrode. And that's really what makes these experiments. This is exactly analogous to what Shobhana said, or the idea of doping. So many times people think of doping as chemical, but it's really kind of a combination of both processes. All you're doing is you're tuning the number of electrons in the Fermi sea. So if you apply a 1 sign of voltage, you can kind of remove electrons, or you apply a positive sign, you induce electrons, and you essentially put more electrons in your system. So this ability to dope it by applying voltage but not applying, in this particular case, doing any chemistry or material science is a powerful way to do experiments. So now let me just quickly contrast with what's interesting. As I told you earlier, this is sort of what we know of our everyday world, and if you take quantum mechanics of electrons in most of solid state physics, this Hamiltonian or this description of energy, which is p square over 2m, is the most popular way to describe electrons in all of solid state physics. Now, on the other hand, in high energy physics, where we talk about particles moving at velocities close to that of light, or in this case, at velocity of light, the Hamiltonian is not this. It's called the Dirac Hamiltonian. This is the Dirac Hamiltonian for massless particles, and c is the velocity of light. And this is the coupling between momentum and spin for relativistic particles. Again, this is for particles which are moving close to the velocity of light, relativistic particles. Now, something unusual happens in graphene is that its Hamiltonian looks analogous to the Hamiltonian in high energy physics of massless Dirac fermions. I want to emphasize that there is nothing relativistic about electrons moving around in graphene. They're moving at about 300 times slower than the electrons slower than the velocity of light. But it just happens that the structure of the crystal, which is honeycomb, tells us that the effective Hamiltonian description of electrons close to the Fermi sea is exactly analogous to that of relativistic particles. So now all the quantum mechanics that is described for electrons in graphene is actually kind of like relativistic quantum mechanics. And that's one of the things why people were really excited about experiments with graphene, because you can do some experiments which were not possible in other systems. Okay, so that's hopefully gives you a clear idea of why graphene is interesting and exciting, particularly for physicists and to some extent material scientists, this perspective. Now I want to say, re-emphasize a point about symmetry to tell you that simple ideas in physics and science are powerful ideas. So I told you the honeycomb structure is that of graphene, and it has a Hamiltonian. And if you're not familiar with the details of it, don't worry about it. Essential is that the energy is proportional to momentum. There is some other physics which I won't talk about today, but it's linear to momentum. Now, there is exactly analogous structure which is of boron nitride, which is boron and nitrogen. So I told you two sides, kind of green and orange earlier. So now boron nitride uses that green and orange coloring. In case of graphene, it is carbon atoms everywhere. In case of boron nitride, that's now different. At one side, you have boron and other nitrogen. So you'll say, oh, that's a huge change. But if you take a step back, as a pair, boron and nitrogen are on either sides of carbon. So as a pair, they have the same number of electrons as a pair of carbon atoms. But its properties are radically different. And they are radically different because this symmetry that you had, if you take this honeycomb lattice and about the center of it, you switch it. You go, say, x goes to minus x. Okay. Then in case of graphene, x goes to minus x, you get back the same electronic lattice about the center of this honeycomb. In case of boron nitrogen and a large class of materials, if you take this x goes to minus x inversion symmetry, not obeyed. If blue cannot be the same as pink. And in case of boron nitride, that symmetry breaks. You cannot, the system is not inversion symmetric. And its Hamiltonian gets modified just because of this breaking of the symmetry, and it actually develops a band gap. So it becomes a semiconductor. In fact, boron nitride is a very good insulator, which has a band gap of about 6 to 7 electron volts. Okay. Okay, so this simple idea that you break the inversion symmetry determines the electronic. So one is a kind of metal, one is an insulate. Okay, now I'm an experimentalist, so I'm always interested in how does one make it. So one of the amazing things about this field is that let me just start this video, is how graphene was made for the Nobel Prize winning. So this is a video from YouTube, and you will find many, where the method by which graphene, one atom thick graphene is made, using something, like a high school project, or maybe even simple. You take a tape and you say, I'm going to peel it off. Okay, so this is not an industrially scalable process. There are alternate methods for making industrial process, but what I want you to take away from this is simple ideas can lead to scientific breakthroughs. Sometimes simple ideas are powerful than many complicated, complex instruments, and this demonstrates that. So if you peel it off with tape many, many times, then randomly on the tape you'll get crystals of graphite which are of different thicknesses. Now, you gently put it on a piece of silicon wafer and you tap it, and some of these crystals will now transfer to silicon wafer, which has a little bit of silicon oxide. I'll explain that a little bit later, why silicon oxide is there. But these are all random events. So this is where experimental science is science, but it also combines art, perseverance of students, and innovation. Okay, so this is sort of an imaging of this, how simply you can see it. Okay, so optical imaging gives you an idea that something is very thin, but it is not a watertight test to say it's 1 atom thick or 2 atom thick. I'm going to tell you in a few slides how you can be sure, scientifically rigorous, about whether it's 1 atom thick or 2 atom thick. Okay, so now this is an image from our lab, and you see that you have a dark blue, kind of purple. The background is a silicon oxide on silicon, and this is thick. It looks silver colored. But here is a triangular flap. You see a triangle, and it's about 25 micrometers. Okay, 25 micrometers by 25 micrometers. So something that I really like to do is, to give a sense for what 25 micrometers is, typical human hair diameter is 100 micrometers. So this length is roughly about 1/4 of the diameter of the hair. Now the idea is very simple. It's thin film interference. Okay, so if you have been to kind of a auto stand or a taxi stand in a monsoon, I'm sure it rains a lot where most of you are, like it rains a lot in Bombay. You'll see in a taxi stand, you'll see films of which are different rainbow colors. And that's basically oil from the auto rickshaw or from the taxi leaking on top of water and forming thin films. And the interference is basically when the thickness of films is an integral multiple of the wavelength, different components of the wavelength, and that's why you get the rainbow color. Exactly the same thing allows 1 atom thick graphene to be seen. You put the graphene and you look at interference of light. Even though this is only a few angstroms thick, it provides enough phase shift for the light so that if you look at different optical paths, that you subtract the optical paths, all the possible, I'm drawing one possible path, you sum them up and you can see a difference in this. And this is a plot of the difference in the light content as a function of silicon thickness, which is the thickness of blue region. This gray region is silicon, which is sort of like a metal for all practical purposes. This is essentially, silicon oxide is glass. It's in a crystalline form, a good quality version of your glass that you see in your windows. And what you see is that at certain thicknesses of silicon oxide, and this is roughly the visible range, so at 300 nanometers or something close to that, 285 nanometers, you see a peak. And that peak means that the difference in the light content from here and here is large. That means the contrast which is difference is contrast, is largest. And so you can see it using simple optical microscope. And that's really the essence. This is something that was figured out by Gaim and Novoselov's group from where the initial research came out. So now I already kind of hinted that, okay, I can narrow down. So you do lots of these experiments. So my student, when they make devices, they make lots of them and then search for them because this is not really kind of a predictable process. So how do we know that something is monolayer? So this technique is something that we are kind of grateful for the discovery of this physics by C.V. Raman, who got from India, who got the Nobel Prize in the last century. Basically, you shine light on any material. So I'm giving you the example of graphene, but this works for any material. So it's the powerful technique for analyzing materials. So you shine light, and then you have a solid. It has atoms which are vibrating around. Okay. And so they exchange some energy with this light. So if the light gets reflected back at the same energy, it's called Rayleigh scattering. But now what can also happen is some light is less energy than the light that comes in. And the other, because some energy is now absorbed by the vibrations of the lattice, and you can also have the opposite process, that energy from the lattice or the atom vibrating is taken away by the light which is reflected back. It's called anti-Stokes. So these red and blue light often have deep information about the vibration of the atoms. And the vibration of the atoms is a very kind of sensitive fingerprint of the material. So it's unique for one atom thick graphite, which is graphene, or two atom, it's quite different. So by doing Raman scattering, you can know whether it's one atom thick or two atom thick. And that's a confirmation test. So this is a very powerful method. It is now in the present time, it's for nanoscience and nanotechnology is one of the most powerful methods. So often you can do on graphene to find out whether it's one atom thick, two atom thick, or even if it has some defect, some atoms are missing, it can actually help you determine. So that hopefully that tells you how we can know that it's one atom thick or two atom thick or three atom thick. It's a very powerful method. So our goal here in these kind of studies is to make electrodes, electrical connections. Again, this triangle is about 25 micrometer. So I have a small video here to show you the broad principle. It's called lithography. It's an idea, a process that is developed in semiconductor fabrication, and that allows you to make very complex devices. I'm showing you kind of a baby version of it. So what you do is you coat a plastic or a polymer on top of whatever, let's say, piece of graphene that you want to make electrical connection to. Then you expose it to a beam of electrons, and that changes the chemical property. And if you can dip it in some other chemicals to remove the plastic from here, and rest of the plastic actually doesn't go away. So what you end up doing is creating holes. These are also called stencils, which are used in arts and crafts. So we are making a stencil out of this polymer layer. And then you evaporate metal, which is made for electrical connections. And then the metal here goes and contacts graphene directly. And now that's basically it. We want to make the electrical connections to graphene. And you want to get rid of all these things. So this can be done by simple chemistry. You dissolve this blue polymer or plastic in a solvent, and the gold on top of it goes away, and all that's left behind is graphene and the electrical connections. So this idea I've shown you using a simple cartoon, but it can be repeated or done in many complex ways. But that's how you make electrical connections, and the end result of making the connections is that you can make a device like this. So this is the same piece before and after making connection. This is just to give you an example, but we make much smaller devices as well for lots of our different studies. Okay, so now I'm going to go a little bit detail. I won't go too much into detail, but I want to give you a flavor for what is exciting and what actually we do. So one of the things that we do in our lab is to study what is called integer quantum Hall effect. Okay, so before I go into integer quantum Hall effect, I'm sure mostly all of the students have heard of Hall effect. They might have studied it in some course in physics or material science, and that's basically if you take a material, let's say graphene, and you basically apply a voltage and you make current and you apply a magnetic field in the perpendicular direction, sort of perpendicular to it, then along the other direction you develop a voltage, and that Hall effect, classical Hall effect, is a very important technique to measure the density of charge carriers. So you have a plane, let's say my phone here, and I apply voltage like this, and I apply a magnetic field like this, and I measure the voltage in this direction. In that voltage is called the Hall voltage. And that's a way to determine the density of charge carriers in any material, whether it's 2D or 3D. And it's used quite a bit. So something unusual happens in the quantum Hall effect, and I'm going to kind of give you an essence of it, flavor of it. So this is a plot of the states that are available. So I showed you earlier this plot, which was vertical, but this is just kind of rotated by 90 degrees. These are states which are available for the electron. So at the Dirac point where the two cones meet each other, states are 0, but as you go away from it, you have more number of states. But they are continuous. There is no gap. One of the interesting things that happens with quantum Hall effect is when you apply large magnetic field, the system does not have a continuous set of states anymore. Okay, it becomes discrete. So this system, which was more like a metal, transforms into a system more like atomic orbitals, which atomic orbitals are not continuous. They are separated in energy. These orbitals are called Landau levels. I won't go too much into it, but the act of applying a magnetic field to this layer, what it does is it makes the electrons go around in circles, just like you would in a Bohr atom. So now if you kind of semi-classically quantize it, you get these energy levels, which are called Landau levels. They're separated in energy, and here you have a gap, means the electron cannot go and sit here. And this is the genesis of the quantum Hall effect. Okay, so you have all these Landau levels, energy levels, and it gives rise to something very peculiar and interesting. So it's a physics associated with two-dimensional electron gases. So you start with two-dimensional electron gas, and then you apply a magnetic field, you get these discrete energy levels, which are called Landau levels. So away from the boundary of the material, edges, the material is an insulator where these energy levels are far below the Fermi energy, and there are no electronic states available. But at the boundary, because the electronic energy levels have nowhere to go, because outside the electron cannot be there, these energy levels will come out and they will cut near the Fermi energy and give rise to these one-dimensional channels. So now we started with a two-dimensional system, and you get two one-dimensional systems on the boundary which are conducting. The orange region is an insulator. And by applying either changing the magnetic field or the density of electrons, you can have only one energy level, Landau level, participating, and you basically get one edge state on either side. So these edge states are very peculiar. You know, they are basically like highways. Electrons on this side can only move in this direction. Electrons on this side can move only in this direction. So there is nothing to kind of slow down this traffic. So they just go happily in one direction and another direction without encountering any obstruction. Okay, these are ballistic. Essentially, they don't encounter any dissipation in their as the electrons move through. And that's sort of at the heart of the quantum Hall effect. If you measure the Hall conductivity, it is actually discrete and quantized. Okay, these steps. This red curve is longitudinal conductivity. It shows peaks. Every time you change the number of Landau levels involved in the below the Fermi energy, you will see a peak, and then you'll see a plateau. And the amazing thing is in the quantum Hall physics is that this is quantized in units of E square over H. E square is the charge of electron and H is the Planck's constant. So it does not depend on the material at all, and it will show steps of 1. And we do a lot of these experiments in our lab. So this, you'll say, why is this interesting? It gives you some important information about the electronic degeneracy of the system. In terms of practical things, these are meteorological standard. The SI system of units that we use, the meter, second, everything. Now, it is now defined in units of the quantum Hall resistance because this value is very precisely known. So this meteorological standard comes out of quantum Hall effect now in the new definition of the SI units. So I'm going to give you a glimpse of the kind of experiments we do. I won't talk a lot about it. It's a bit technical, but I want to give you a flavor that we can do cutting edge research with these kind of devices. So the kind of experiment we do is we apply magnetic fields. These are experiments done at low temperature, around 1 Kelvin, and large magnetic fields are applied. And we measure resistance or conductance of the material as a function of gate voltage, which is the density of charge carriers. And we can tune the charge carriers. And these lines, so this plot is a matrix, numbers visualized using color. So number of the conductance or resistance is visualized by color because it's a large data set. It just becomes more easy to visualize the large data set. And if I plot, take a line, you'll see peaks or valleys in the value of conductance. Now, these lines are basically the Landau levels from the quantum Hall effect, and we can extract information about the degeneracies in the system. If I plot the GXY, which is the Hall conductivity, it shows discrete steps. It's not continuous. So sometimes you'll see a step of 2 or 1 here, and then here you'll see a step of 2, and then here you'll see a step of 4. And the magnitude of the steps tells you about the degeneracy, how degenerate the individual Landau level is, whether it is degenerate with 1 or 2 or 4. That provides information about what's going on in the electronic system. Here, for example, at large magnetic field, you'll see that degeneracy is completely lifted and GXY is units of 1 E square over H. Okay. All right, so that gives you a flavor of the one kind of physics that we study. And we have been, let me look at the time, and I want to give some time for questions. So maybe Professor Kalita, can you tell me how much time do I have? And then I can maybe...
Yeah, you can take, I think it is going to be 12, right? You can take 5-10 minutes more, no issue.
Okay, all right. So what I'll do is I'm going to skip the next part a little bit just to, I want more questions and participation. So I'm going to skip the next part and talk about 2D superconductors. Okay, maybe I'll go with this few layers of graphene, and I won't talk about 2D superconductors because it's a one connection. Okay, so let me just go ahead and I'll try to wrap up in about 5 minutes. Okay, so now many of the electronic devices that we study are based on simple ideas. One of the simple ideas that people figured out, and this has connection to quantum mechanics that you might have studied, or solid state physics, is that you might have studied what is called a chronic penny model, which is basically if you have a potential barrier in quantum mechanics and you have electron coming from here, then there is some probability for transmission, reflection, electron go some transmission on the other side, and then you have if you have a periodicity of these regularly arranged ones, then this is basically a kind of a periodic potential. Okay, so that's the chronic penny model, and you look at the electronic properties of this kind of, it is different from one which does not have any potential, which is periodically arranged. And this is a way to change the electronic properties of different systems. So if my initial energy momentum relationship was this parabola, I'm not talking about graphene right now, then introducing this array of periodic defects essentially generates some additional periodicity or scattering at each of these barriers, and that opens up gaps. So it opens up a gap here, it opens up a gap here, and so on. So now the material which was metal-like in this region will now suddenly become a semiconducting-like region in this energy window. So this is a way to engineer or to tailor the electronic properties of material. So this strategy is at the heart of solid-state physics. Many of these key developments happen in 1970s, and these kind of semiconductors, this is a cross-section of it. So imagine I have a phone and I look at the edge of the phone. I will see many, many layers of semiconductors, and this is a scale bar to give you an idea, 10 nanometers. This is much longer than the atomic spacing. Atomic spacing is of the order of an angstrom, which is about 0.1 nanometer. So why people made these kind of things is that you can make new kind of electronic devices. These particular devices are made by a method called molecular beam epitaxy for semiconductor growth. So it's like you take a bread, which is this black layer, then you put some jam, which is this light gray layer, then you put another slice of bread, and then another layer of jam, and so on. And you make a giant sandwich that will give you this semiconductor. And this kind of heterostructure will give rise to new electronic property. So in the last 1 year, another 2 years, there has been a kind of a new idea in two-dimensional crystals, which has never been explored before in solid-state physics. There are often statements like this in physics where people say that there is a new development. So this is truly a new development because of 2D crystals. Is that imagine you might have experienced this if you are sitting in a room with a mesh, and let's say you have another mesh in your hand, a jali, and you rotate that jali around, you'll see patterns developing, and that's the kind of pattern that you see. You have one layer which is purple color and one is light blue, and you rotate them relative to each other, you basically get patterns. And these patterns are called Moiré patterns, and you can now realize superlattice, like the one I showed you, that was through the cross-section of the device. Now here you can realize in the plane. And this has, in the last 2 years, led to a lot of new exciting activity, and we are working on this physics. So this kind of a nice video shows the effect. So if I rotate these two layers relative to each other, you will see a pattern emerge, and the pattern length changes as the angle of rotation is changed. Okay, so that means the superlattice that I showed you earlier, which is a lattice which is longer than the atomic spacing, it can now be tuned by changing the rotation angle between two layers. And that's a new idea. What people have discovered is that, and this is not our work, we are doing something related, which I'll show you, is that if you take two layers of graphene and you rotate them relative to each other by 1 degree, you can actually see the superconductivity in 2 layers of graphene. These are called twisted bilayer graphene. This is very unusual because most of solid-state physics thought that we have to have some kind of metals and alloys to realize superconductivity. Now, this is superconductivity which is intrinsic to only layers of carbon, which has never been seen before. So now, some simple discovery like peeling off layers of graphite and realizing one graphene has led to an idea that if you rotate two layers relative to each other, you can now see physics which has not been seen before. Okay, so now how does one, I'm going to end with in a couple of slides, how does one make something like a twisted layer? So many groups follow different techniques. We have developed our own method to make these kind of devices. So what we do is, because we want to realize layers which are rotated by a precise angle like 1 degree, what you do is you start with one sheet of graphene, you cut it with a kind of you can think of it as a scalpel, which is sort of what we figured out. And you cut it into 2 pieces using this very sharp scalpel. So this is one sheet of graphene. You cut it into two pieces. Now, because this graphene was part of the same sort of structure, they are aligned completely. So then what you do is you basically pick up one layer, okay, on a piece of rubber. Then one layer goes away, the other cut part remains behind. Then you bring rotate the lower one by a precise angle that you want, 1 degree, 2 degrees, whatever you want. And then these two layers are now rotated by a precise angle. And then you bring them in contact and you pick this up layer. So these graphene layers like to stick to each other preferentially. So now you have realized a layer of two which has a precise rotation angle between them. And then you can make some complex devices. So this is much more complex than the earlier device that I showed you. This is a scale bar, 20 micrometers, about 1/5 of human hair diameter. And these are all electrical connections for doing electronic measurements. And the way this device is made is that it has this region of twisted graphene. Our work has focused in the last 1 year on twisted bilayer. So essentially, bilayer graphene cut and rotated relative to another bilayer graphene, and then you sandwich it in layers of an insulator. Okay. So I won't give you lots more details, but what this arrangement realizes is a system which is basically a semiconductor which can be tuned, like atomic orbitals getting narrower and narrower. And so that's one of the reasons why these systems are interesting, because they're very narrow. So I told you about these things. I'm going to stop now, and hopefully you'll have some questions for me that I would love to answer. So I think I'll stop now, and I'm open to the questions. Thank you very much for your kind attention.
Thank you, sir. So, anyone?
Ma'am, I have a question.
Yeah.
Sir,
Yeah.
First of all, it was a very good presentation. So, sir, I would like to ask you how you are rotating or twisting the graphene layer.
Okay, so that's actually pretty straightforward. Let me just share the screen again. So, see, imagine that this part, this whole assembly is sitting on a stage which has a rotator underneath it. It is based on gear mechanism. So, imagine a gear, if you're familiar with any rotation mechanism in a mechanical workshop, you can have a gear which can rotate precisely by 0.01 degree without any problem. So what we have is under the stage, we have a rotator, precise rotator that rotates it by an known angle. So this is the rotation mechanism itself is very old technology. It's maybe a century old. Okay, we just employ a stage which has this rotator. Does that make sense?
Yes, sir. Thank you, sir. Sir, and I also like to ask you, what is the tool you are using to cut the slices of the graphene? Which tool you are using?
Okay, so the details are in this paper. So if you go to if you search my webpage, our group webpage, you'll find a publication which has details and even a video. If you cannot find, you email me. It's basically an optical fiber which is tapered, which is pulled. So this pulling or tapering of optical fiber is a well-known technology. So we just used it here. There are other methods that other people use. They even use an AFM, but we find this to be a more high throughput technique to make devices.
So regarding that twisted bilayer graphene, so that does the twisting depend on the operating conditions like pressure, temperature, etc.?
Okay, so these are good questions. So we dial in the angle we want. Let's say we want typically around 1.1. It depends on the physics, because I told you that the electronic properties are controlled by the relative twisting. So we have to have some idea about where we are going. Like as in, we have to have some target rotation. So sometimes there is some, you remember these atomic crystals at a rotation angle of 1 degree, that's not a stable, thermodynamically stable configuration. But so sometimes we get some variation from it, but we make lots and lots of devices. And then we have a way to identify from the electronic measurement what the actual angle is. So there is no randomness or guesswork of what the angle is. The electrical measurement tells us what the angle is. Okay. So parameters like temperature and can play a role. This is not understood. I told you that this field is relatively young, only 2 years old. This field, so people are still trying to understand how to stabilize. How to stabilize two layers which are only 1 atom thick by an angle of rotation which is kind of strange, 1 degree. It's not a stable configuration.
Yes.
I hope that answers your question.
Yeah. So one more question, sir, from my side. In slide 14, you have shown the quantum Hall conductivity, right? So, and it was mentioned that it is independent of the material.
Yeah.
Am I correct?
Yes, that's right.
Yeah.
It's this is conductance. Okay, so there's something you have to be a little bit careful when you talk about conductance, conductivity in 2 dimensions. Conductance and conductivity have same dimension. Electrically, they are both units are ohms.
Okay.
So this is conductance, which can be connected to the conductivity, but they are all quantized in units of E square over h.
Yeah.
There is no material property which comes in.
Okay. So
at least within the integer quantum Hall effect.
Yeah. So there are materials of metal oxides, 2-dimensional materials, which are having basically the honeycomb structure as that of graphene. So can we expect those materials showing similar?
Yeah. So I don't know specifically the material that you're talking about, but people have seen in metal oxides, lanthanum, strontium oxides interfaces. People have also realized electron gases. People have not isolated in 1 atom thick thus far. I am not aware of it. But people have grown heterostructures by molecular beam epitaxy and made an electron gas at the interface of 2 oxide interfaces. There people have seen quantum Hall effect, and it's exactly like this. So this is not a material dependent property. This is very fundamental. I did not get a chance to talk a lot about it, but if you have heard about new ideas in physics, which is of topology aspects of condensed matter, these are all in some sense, quantum Hall effect is the mother of all those quantum topological ideas in condensed matter.
Yes. So is there some any theoretical work available in this area? Are you aware of?
Yeah. So this is one of the most productive areas of condensed matter research, or I would say, in research in physics, it would be very high. There are lots of papers every day. So one easy way is archive. Other is if you have some specific questions, you can email me. I can send you some papers. But if archive is is a very good resource, you'll find something like 10 papers every day on these topics, topological ideas of condensed matter, and particularly on twistronics, which is these twisted layers.
Yes, thank you very much, sir.
Yeah.
Hello, sir.
Yeah, please go ahead. Yeah.
Actually, I have some question regarding the quantum Hall effect, which you have said a few minutes ago. First of all, the presentation is very beautiful, sir. Thank you for that. And basically, I want to know when you have basically considered the quantum Hall effect, what type of state you have considered, whether it is a chiral state or helical stages.
Okay, so seems like you know a lot more details, which I have not skipped. But so these are not these are simple integer quantum Hall states. I'm not really talking about. So quantum Hall, integer quantum Hall itself is, in some sense, has a chirality associated with it. For a direction of magnetic field of one sign, the edge states are always flowing in one direction. Helical edge states can be formed under special conditions based on what these two states are and what happens at the boundary. At this point, in this discussion, it may not be helpful for others. Maybe we should have a separate conversation, or you can send me an email and we can have a discussion. But we study that quite a bit in our work, but it might be too much technical for the rest of the people.
Okay. Sir, one more thing. Is there any deformation in the Dirac cones which you have shown?
Is there any information in the Dirac cones, as in?
No, sir.
What information?
No, sir. I want to know: is there any deformation in the Dirac cones in quantum Hall effect?
Okay. No. Quantum Hall effect doesn't really change any deformation of the Dirac cones. If your question was slightly different, which is also a valid question, how accurate is this Hamiltonian for the description of electrons in graphene? And the answer to that question, even without quantum Hall effect, it's a very good description. It's very, very good. People have experimentally tested it, that this Hamiltonian is a very, very, very good description. There are regimes under which one can see deviations from it, but it's a very good Hamiltonian.
Sir, what Hamiltonian you are considering? Kane Hamiltonian or something else?
Sorry?
Sir, you are considering Kane Hamiltonian or something else for that purpose?
No, this is a simple Hamiltonian. This is just simple coming out of, you can get it out of tight binding. You don't need to invoke Kane and Mealy model yet.
Yeah. Okay, sir. Okay. Thank you, sir. Sure,
okay. So I would love some questions from students. I would love some questions from students. I have some questions in the chat box.
Yes.
So, I am happy to answer lots of other questions from, but I would love some questions from students. So, please go ahead. So, students, if you're still around after a long set of talks.
One scholar has posted one question in YouTube. Actually, she's asking. Yes, he has transferred the question here. So, how can we pick up single layer of graphene?
Okay, good question. This is very nice. So, so graphene, these layered materials like to stick to other layered materials. It's called van der Waals interaction, preferentially. So, one way to preferentially pick up layer of graphene is to bring a layer of boron nitride. It can be few crystals thick, a few layers thick. Am I still presenting? No. Okay. You can bring it in contact, and graphene, if it's sitting on silicon oxide, will preferentially like to stick to boron nitride. So you bring a material, you look from the top with an optical microscope, you align it, and then you can pick it up. Does that answer your question?
So she is not available here in this meeting.
Okay. Okay, so hopefully it does. If it does not, please feel free to email me. I'm happy to give more details about this. So I'm ready for the next question.
Hello, sir. This is Mustako from Department of Physics. So I have a few queries. As a different human eye has different visibility level. So is it possible to sharply confirm the single monolayer, a single graphene layer or two atomic graphene layers through the optical microscope by seeing the contrast level?
So you can narrow down. So it's experimental science is an art. A part of it is science, but the actual implementation of making devices, doing experiments in the lab, is kind of skill. And once you do it many times, you can sometimes have some error in saying whether it's monolayer or bilayer, but people who are good in the lab, like most of my students are much, they're much smarter than I am. They can basically easily identify whether it's mono or bi. Then we do some other tests. But it's a skill. So you can train yourself to identify layers very accurately. I think ability to see is a little bit, individual ability to see is sort of does not come into the picture, because often we don't really necessarily see with our own eyes, but we use cameras, digital cameras.
Okay.
And let me say that even the cheapest digital camera that you kind of install on your microscope, sometimes even the mobile phone, will be able to detect these monolayer graphene layers. So have I answered? It's a long answer to your question, but have I answered it? So
can I move to my second query?
Okay. Yeah, sure. Maybe
it's a very short one. So suppose I prepare graphene in a chemical solution and I want to extract that graphene to another platform. Or like you did, the rotation of the small pieces of graphene. So while I'm transferring or rotating the small pieces of graphene, so it seems to be this process is going to insert some defect or deformations in the graphene shape. So how to avoid this kind of effect?
We don't. Yeah, so it's a good question. We don't do anything solution based, primarily because for electronic properties and electronic devices, when you take something out of the solution, there are all kinds of I would say not imperfections but residues of the solution and things that are in the solution. So we don't do any wet chemistry. In fact, we try extra hard to make sure that the layers of graphene never ever see any liquid or water. Okay. Now, if you start from a liquid, the way you are proposing of twisted layer, I don't see a way out. It will be a very messy method, and you have no control. The advantage of putting something on a surface is that manipulation, because these are one atomic layer doesn't have much rigidity. So it can bend and fold, which happens all the time, even though it's supported on a substrate. Doing it from a liquid to twisted, I wouldn't say impossible, but it's extremely hard. So I wouldn't do it. You can think of other ways to first get it out of the solution, then make sure that it's clean, and then try to make devices. But doing it in solution is a difficult situation. I would not recommend it.
So my last question is, yes, thank you, sir. The last question is,
we can take
some students, please.
Yeah, one question. Yeah. So one question from a student. What are the importance of two-dimensional materials?
Okay. All right. So this is a very broad question, and so while I told you that there's a lot of interesting things you can do with two-dimensional materials for scientific work, in terms of importance, there are a lot of possibilities. So if you say what are the applications that are already out there, there are limited examples that I can give. But what is important, the potential of these materials in doing things which were not possible earlier is high. And so they can be used for, as Shobana mentioned earlier in her talk, and I think she's involved in some research, some catalysis can be done with these 2D materials and particular kind of 2D materials with different crystal structure. That's a possibility. You can make electronic devices like transistors, photodetectors, So there's a lot of possibility, but in terms of scientific things, I think there is a lot more interesting things, like, this idea that you can rotate 2 layers of material. This is not possible ever before. So in terms of application, there's a huge potential for making detectors. There is already, I think, significant work on composites, which is taking 2D materials and blending them with polymers to make materials which are extra hard or have strength properties. But it's relatively early to say there are concrete products for it, but there's a huge potential. I hope that answers the question. So there's another question which says why graphene is so important, unique compared to other 2D materials, because we have seen so many works on graphene and not on other 2D materials. Okay, so that's a good question. In this talk, I focused on graphene because that's sort of focus of our work. We work on other systems, 2D materials. I didn't get a chance to talk about it in the last part. We work on superconductors. There is a lot of research on several different aspects. It's extremely competitive area. So I would say that anything that can be made into 2D layers is being explored. And so my talk was biased for graphene because I work in it. So it's my personal bias to some extent, but it's not true. A lot of work is on other 2D semiconductors like dichalcogenides, which is molybdenum disulfide, tungsten disulfide, tungsten diselenide, and some superconductors, and now magnets also. There are 2D magnets. So there's a lot of works. Please don't infer from my talk that this is a definitive situation of the scientific community, but it's more of what my focus right now is. Okay, so I hope that clarifies things. Now there's another student from Rimpisa. Her question is, as de Broglie wavelength Fermi level determines dimensionality of electronic property for optical and magnetic property, what are the other parameters? So that's a good question. For optical properties, you can think of the Bohr radius for excitons as determining the length scale. For magnetic properties, depending on what kind of magnetic property that one is talking about, one can look at the stiffness of, say, spin waves. So you have to ask what specific property that you're interested in looking at, and you look at it a little bit more carefully, the physics of it, you'll be able to figure out what the parameters are. So there's no a magical table that you look at and say, okay, this is this. The physics that you're exploring or the science that you're exploring determines this criterion of dimensionality. I hope that answers your question. Okay, so there's another question from another student, Asha Mani, and the question is: graphene don't have a band gap. Does it create problem when you try by moving the Fermi energy in the gap? And that's a problem for graphene, monolayer graphene, particularly because it doesn't have a band gap. You cannot turn its flow off. So you can change the amount of flow of electrons in a transistor. So if there are 1,000 going, then you can squeeze it to 1 electron, let's say, per unit time, and but you cannot turn it off. So a leaky tap is not a good tap for electronic devices because it drains the batteries. But there's no reason for being despondent. There are other materials like graphene which have a band gap. I already kind of mentioned a little bit materials like MOS2, which have a band gap of about 1 electron volts roughly. So they don't have some other properties which are nice, but they are very close cousins of graphene, and they have, it's improving day by day, but they have pretty good mobility as well. So there are different materials. So graphene is not an answer to everything. What it has done is that it has opened avenues for using that strategy to study different materials. Okay, I hope that answers the question. So as far as the chat box is concerned, I think I have answered all the questions related to my talk. So if there are maybe one or two more questions, I can address them. There was somebody had another question which I sort of didn't answer to address the question of the students. Yeah, maybe if you have one question, you can go ahead.
Last question: what is the typical thickness of metal electrode that has been coated on the graphene?
Yeah, it's about it's not a fixed quantity, but it's like 50 nanometers, 50 to 100 nanometers. Okay. 50 to 100.
Thank you, sir.
So if there is no more question,
hello, ma'am. Hello.
Okay, Chandan. Yeah.
Oh, if there is no problem, I have a small question. Actually, not related to this material science. This is actually not related to material science. You mentioned about some massless Dirac fermion, right?
Yeah.
Yeah, I just want to know, does it signify some physical particle or just a theoretical concept?
Oh, good. Okay, that's a very good question. So, is this so in solid state physics? Yes. This thing comes up. So, thank you for asking. Let me just share the screen. It's a good question. Okay, so thanks for asking this question. It's a good question and a deep question. Your question will be helpful to a lot of people. Okay, so now we know that the fundamental particle in solid state physics is the electron. Okay. Now, when we talk about electrons in a lattice, in a kind of lattice with particular symmetry, and we construct essentially the electronic states that are allowed, that's when you get these bands. Okay?
Yes.
These are electronic states of the fundamental particle that is electron. Okay? Then, as I told you, that if I want to look at excitations close to the Fermi energy, okay, then the picture becomes this. So there lies the answer to your important question, that this Dirac fermion is an emergent property of the electron in the lattice. Okay, so it's a quasi-particle. So this is not a fundamental particle in the sense that you asked the question, but it's the property of the electron that belongs to the honeycomb lattice. So it's an excitation of the electron in this solid. You can't take it out of the lattice. The moment you take it out of the lattice, you basically get you project it into an electron, a normal electron that you know. So these excitations are collective excitations. So in solid state physics, you'll find lots of it. So before I go there, let me just say that, this in a narrow range of energy, something like 100 milli electron volts, this description of massless Dirac fermion is valid. Okay. Now, if I shine light on it, then I will sample these bands, higher bands, and this is certainly not a massless Dirac band. Okay, so this Hamiltonian that I write is an effective low energy Hamiltonian. These are keywords which are often solid state physics people, because they know this, they've kind of skipped this, but for an outsider, this Hamiltonian is not a global Hamiltonian that describes the properties of the material. but it's a low energy excitation. This Hamiltonian is a low energy excitation close to the Fermi energy. So it's an emergent property. And this happens in solid state physics all the time. And one other candidate we know is phonon, which is a quanta of vibrations in a lattice. It's not a fundamental particle. It's a collective excitation of the lattice. Then magnon. A magnon is a collective property of the magnetic lattice.
Yes. Actually, in elementary particle physics, such kind of particle does not exist, right? Till now. Neutrino was a candidate, but it is now massive. It is found. So that's why I was asking. Okay, thank you, sir.
Sure. Yeah, it's a good question. Thank you for asking that question because it can be helpful to others as well.
Welcome, sir.
So, if there is no more question, because already we have taken, I think, 20 extra minutes from you, sir. It was
It's a pleasure.
Yeah, it was a wonderful presentation. Indeed, it was a great opportunity to hear you, sir. So we expect such occasions to hear you again. So actually, on the behalf of the organizers, personally, I thank both the speakers of today's event. They had very good, very wonderful, excellent presentations. And Shobna, I personally know her because I was with her for 1 year as a postdoctoral student. So there was a little bit of technical issues in between, but overall it was very good. And I'm sure that if students get opportunity to interact with you, ma'am, definitely they will learn a lot. And thank you once again, Shobna madam, as well as Desmukh sir. Now I would like to invite the head of the Department of Physics, Dibrugarh University, Dr. Pankaj Datta sir, to offer the vote of thanks.
A very good afternoon to all. Hello, am I audible, Gulawani?
Yes.
Yeah. So it's a pleasure for me to offer the official vote of thanks on this very special occasion of the department. So first of all, I would like to thank Professor Deepak Setia sir, the Dean, Research and Development, Dibrugarh University, for being with us today. We are grateful to you, sir, for your lecture, inaugural lecture, and also for your views on Teachers' Day education system and sharing your experience with Professor S.V. Singh, sir. We are fortunate to have Professor Subna Narasimhan as our speaker today. We thank you, madam, for your very valuable time and also sharing your work among the students and participants. I am sure that students have gathered a lot from your very informative and interesting lecture. Madam, we will be looking forward to you for our next endeavors as well, and we'll be seeking your guidance and support. Our gratitude goes to Professor Desmukh sir for his very energetic and exciting talk on 2D materials. I am sure all the participants felt a very good flavor of experimental science from your lecture. We thank you for being with us in spite of your very busy schedule. We'll be definitely look forward to you in future occasions of the department as well. I would like to thank all the participants, panelists who have joined us through Google Meet and YouTube today. Your participations had really made the program an enjoyable one. My sincere thanks goes to the faculty members of the Department of Physics for their effort to make this program a successful one, especially to Dr. Bulumoni and Dr. Gori. They have done a very hard work for organizing this particular event. Our sincere thanks goes to Dibrugarh University Authority for their support and guidance. Thanks goes to Karunakar Bora, Technical Officer, Dibrugarh University, for the very nice arrangement associated with this program. Last but not least, I would like to thank all those whose names might not be coming to my mind at this moment, but are associated with this program. So I thank you all again for your presence and support. So here actually we come to the end of, or the conclusion of this particular Professor S.L. Das and Professor S.B. Singh Memorial Lecture 2020. So we will seek similar support from you in our next editions as well. Thank you all. Over to Buluman.
Yes, so the meeting has come to an end. We are really thankful, especially to the speakers, because you have spent more than 3 hours in this meeting, in spite of your busy schedules. So thank you once again. Look forward for your future interactions. Thank you once again. So goodbye to all from my side.
Yeah, thank you. I enjoyed it. Yeah.
Thank you, Bulumoni, and
Yeah, she has got the network issue. Anyway, she could manage at least, right? Professor Deshmukh? Yeah.
Yeah. Okay. All right. Thank you very much. I enjoyed it, and best wishes to all of you.
Thank you. Thank you.
Sir.
I will leave now. Yeah. Okay. Bye.
Bye.